When most people think about rockets, the logic feels almost obvious. Almost too simple, the question. If you want to go higher, you add more fuel. If you want to go faster, you add even more. It is the same instinct we use in everyday life. A car runs longer when you fill the tank. A plane flies farther when it carries more fuel. More fuel means more distance, more power, more capability. It feels like a straight line, a simple cause and effect. And at first glance, rockets seem like they should follow the exact same rule. But here's where things begin to quietly fall apart. A rocket is not just moving forward through air like a car or a plane. It is trying to escape Earth itself. There are no roads, no lift from wings, no atmosphere to push against in the same way. A rocket must carry everything it needs from the very beginning. Every drop of fuel, every kilogram of structure, every piece of payload, all of it must be lifted at once from the ground against gravity all the way into space. So when you say just add more fuel, you are not just adding energy, you are also adding weight, and not a small amount of weight, but an enormous one. Fuel is heavy. In fact, it quickly becomes the heaviest part of the entire system. The moment you add more fuel to go farther, you have also made the rocket heavier, which means it now requires more force just to lift off the ground. At this point, the intuition still tries to hold on. You might think, that is fine. Just add even more fuel to compensate for the extra weight. But this is where the illusion deepens, because that extra fuel you just added also has weight. And now you need even more fuel to lift that additional fuel. And if you follow this logic just a few steps further, something strange begins to happen. Every time you try to solve the problem by adding fuel, you are actually making the problem bigger. Imagine trying to carry supplies for a long journey. You pack food so you can survive the trip, but now your bag is heavier, so you burn more energy while walking. That means you need even more food to compensate. But that extra food adds even more weight, which again increases how much energy you need. Very quickly, you are no longer just carrying food for the journey. You are carrying food to carry the food. And the longer the journey, the worse this problem becomes. Rockets face this exact dilemma, but on a much more extreme scale. When a rocket launches, a large portion of its fuel is not being used to push the payload into space. It is being used to lift the fuel that has not been burned yet. In other words, the rocket is spending energy just to move its own energy source. This is a deeply unintuitive idea, because we usually think of fuel as something that helps us move forward, not something that creates an additional burden we must constantly overcome. And yet, this is the reality of rocket flight. At the very beginning of the launch, the rocket is at its heaviest. It is carrying all of its fuel at once. The engines must generate enough thrust not only to overcome gravity, but also to accelerate this massive weight upward. As the rocket burns fuel, it becomes lighter, and the job becomes easier. But getting to that point requires an enormous amount of energy up front. So the simple idea of just adding more fuel starts to reveal its hidden flaw. It assumes that fuel only helps, when in fact, fuel also hurts. It gives you the ability to accelerate, but at the same time, it increases the amount you need to accelerate. It is both the solution and the problem, all at once. And this is where the illusion truly breaks. Because if adding fuel always makes the rocket heavier, and a heavier rocket always needs more fuel, then you are no longer dealing with a simple linear system. You are stepping into a feedback loop, one where every attempt to improve performance comes with a cost that grows faster than you expect. At first, this effect is easy to ignore. For small increases, it seems manageable. But as you push further, as you try to reach higher speeds and greater distances, the relationship between fuel and performance begins to change dramatically. What once felt like a straightforward solution slowly transforms into a trap. And the deeper you go, the harder it becomes to escape. At this point, the problem starts to sharpen into something much more concrete. It is no longer just an abstract idea that more fuel makes a rocket heavier. It becomes a physical barrier, something you can almost feel pressing down on the launch pad before the rocket even moves. Because weight is not just a number. It is the very thing the rocket must fight against from the very first second. When a rocket sits on the ground, gravity is pulling every kilogram of its mass downward. The engines must produce enough thrust to overcome that force, or the rocket simply does not leave the ground. This creates the first and most unforgiving requirement. Before a rocket can go anywhere, it must already be powerful enough to lift its entire mass, including all the fuel it carries. Now imagine what happens when you add more fuel. The total mass increases, which means gravity pulls harder. To compensate, the engines must generate more thrust. But thrust does not come from nowhere. It comes from burning fuel at a high rate, ejecting mass downward to push the rocket upward. So in order to lift a heavier rocket, you need to burn more fuel per second. But here is where the situation becomes more complicated. You are not just adding fuel to increase total energy. You are also increasing the rate at which that energy must be used. A heavier rocket demands stronger thrust, and stronger thrust demands faster fuel consumption. So not only do you need more fuel overall, you also need to burn it more aggressively just to get off the ground. This creates a tension at the heart of rocket design. On one side, you want to carry as much fuel as possible so you can reach higher speeds and travel farther. On the other side, every extra kilogram makes liftoff harder, forcing you to spend more energy just to begin the journey. The rocket is caught between these two opposing pressures, and there's no simple way to balance them. To see how extreme this becomes, consider the very beginning of a launch. The rocket is at its maximum mass, fully loaded with fuel. The engines ignite, producing an immense amount of thrust, but for a brief moment, the rocket barely moves. All that power is being used just to counteract gravity and inertia. It is like trying to lift an impossibly heavy object. You push with everything you have, but at first, nothing seems to happen. Only when the thrust slightly exceeds the weight does the rocket begin to rise. And even then, it does not shoot upward instantly. It climbs slowly, almost reluctantly, as if it is struggling against its own mass. This is the cost of carrying so much fuel. The rocket spends a significant portion of its energy just overcoming the burden it brought with it. As the rocket ascends and burns fuel, its mass gradually decreases. This is the one advantage it has. Every second, it becomes lighter, and the same engines now have an easier job. Acceleration increases, and the rocket begins to gain speed more efficiently. But this improvement only comes after an enormous upfront investment of energy, all spent just to get past the initial weight. And this leads to a crucial realization. Not all fuel is equal in its usefulness. The fuel burned later in the flight is far more efficient because it is pushing a lighter rocket. The fuel burned at the beginning is the least efficient because it is spent lifting the entire system. including all the fuel that has not yet been used. So in a very real sense, the rocket is forced to waste energy at the start, simply because of how much mass it carries. And the more fuel you add, the worse this imbalance becomes. You are increasing the portion of fuel that exists only to support the rest, rather than to directly contribute to reaching space. This is the hidden cost of weight. It is not just that heavier rockets need more energy. It is that they need to spend that energy at the worst possible time, when the burden is greatest and the efficiency is lowest. Every additional kilogram amplifies this effect, making the system more demanding, more fragile, and more dependent on precise engineering. And now the original intuition begins to completely break down. Adding more fuel does not simply extend your capability. It reshapes the entire problem. It changes how much thrust you need, how quickly you must burn fuel, and how efficiently that fuel can be used. It turns what seemed like a straightforward solution into a delicate balancing act, because at the heart of it all, the rocket is not just fighting gravity. It is fighting its own weight. At first, the problem feels manageable. You add a bit more fuel. The rocket gets a bit heavier. And you compensate with a bit more thrust. Everything still seems under control. But the deeper you go, the more the system begins to behave in a way that feels almost unfair. Because this is not a simple trade. It is not one step forward for one step back. It is a loop. And that loop begins to grow faster than intuition can keep up with. Imagine you want the rocket to go just a little bit faster, not dramatically faster, just enough to reach a slightly higher speed. The natural response is simple. Add more fuel. That extra fuel will burn, produce more thrust, and give the rocket the additional velocity you need. But the moment you add that fuel, you have already changed the starting condition. The rocket is now heavier, which means it needs more energy just to begin the journey. So you adjust again. You add a little more fuel to compensate for the extra weight, but that new fuel also adds weight, which means once again, you are forced to add even more. What started as a small adjustment begins to spiral outward. Each solution creates a new problem, and each new problem requires an even larger solution. This is where the loop reveals itself. You are no longer adding fuel to improve performance. You are adding fuel to support the fuel you just added, and then you're adding more fuel to support that. The purpose begins to blur. Instead of pushing the rocket forward, more and more the system exists just to sustain itself. To make this clearer, think about carrying supplies on an endless journey. You pack food to survive the trip, but that food adds weight. So you need more food to sustain the extra effort. Then that extra food requires even more food, and the cycle continues. At some point, most of what you are carrying is not helping you reach your destination. It is just helping you carry the rest. Rockets face this exact situation, but at a scale that is far more extreme. The further you want to go, or the faster you want to travel, the more severe this loop becomes. Small increases in desired performance demand disproportionately large increases in fuel. What feels like a modest upgrade quickly turns into a massive redesign. And here is the part that makes this loop so dangerous. It does not grow in a straight line. It grows faster than that. Each layer of added fuel compounds the problem because it increases both the mass and the energy required to move that mass. The system begins to behave exponentially, even if you never use that word. You feel it in the way everything escalates at first. You are adding fuel to solve a problem. Then you are adding fuel to solve the problems created by the previous fuel. And eventually, you are adding fuel mostly to deal with the weight of fuel itself. The original goal, reaching higher speed or greater distance, becomes harder to see. Buried under layers of necessity, this is why rockets end up looking the way they do. Long, towering structures, dominated not by the payload they carry, but by the fuel required to make the journey possible. And even then, they are operating right at the edge of what physics allows. There is no excess, no comfort, only careful balance. The loop never truly stops. It only becomes constrained by reality, by engineering limits, by materials, by cost. You cannot add fuel forever, because at some point, the rocket becomes too heavy to lift at all. The system collapses under its own weight before it even has a chance to begin, and now the illusion from the beginning is completely gone. Adding more fuel is no longer a simple solution. It is a decision that pulls you deeper into a system where every gain comes with a larger cost. A system where progress feeds on itself, and where the line between solution and problem disappears. This is the loop that never ends. And once you are inside it, every step forward demands more than the last. At this point, the loop is no longer just an observation. It becomes something deeper, something that can be described, predicted, and ultimately something that cannot be escaped. Because behind all of this, behind the weight, behind the fuel, behind the endless loop, there is a rule, a quiet rule that governs everything a rocket can and cannot do. This rule is known as the rocket equation. It does not look dramatic at first. It is just a relationship, a connection between how fast a rocket can go and how much of its mass is made of fuel. But hidden inside it is a truth that explains everything you have just seen. And more importantly, why the problem keeps getting worse the further you push it. The key idea is not about how much fuel you have, but how much your mass changes during the flight. A rocket starts heavy, full of fuel, and ends lighter after burning it. And the difference between those two states is what determines how much velocity the rocket can gain. Not the total fuel alone, but the ratio between what you start with and what you end with. And this is where the trap reveals itself. If you want to go faster, you need to increase that ratio. You need a much larger starting mass compared to your final mass. In simple terms, you need to carry far more fuel relative to everything else. But increasing that ratio is not easy, because every unit of fuel you add increases the starting mass and makes it harder to push the rocket in the first place. So you push further, you add more fuel, trying to increase the ratio, but the effect is not linear. You do not get double the speed by doubling the fuel. You get far less than you expect. And if you want just a little bit more speed beyond that, the amount of fuel you need begins to explode. This is the core of the trap. Each increase in desired velocity demands a disproportionately large increase in fuel. Small gains become expensive. Moderate gains become extreme. And eventually, even tiny improvements require enormous amounts of additional mass. The system becomes unforgiving. And there is no clever trick inside the equation to change that. It is not a limitation of technology. It is not because engines are inefficient. It is not because materials are weak, even with perfect engines, even with ideal conditions. The structure of the equation itself forces this behavior. It is built into the physics of how rockets work. And suddenly everything from before makes sense. The weight problem, the inefficient early fuel, the endless loop, All of it comes from this one relationship. The rocket is not just carrying fuel to go forward. It is trying to maintain a ratio that becomes harder and harder to achieve. Every extra kilogram pushes the system further away from that goal, even as you try to move closer. This is why rockets are dominated by fuel, not because engineers want them to be, but because the equation demands it. If you do not carry enough fuel, you simply cannot reach the speeds required to stay in orbit or escape Earth. But if you try to carry more, the cost rises faster than you can manage. You are trapped between two realities. Too little fuel, and you fail to reach your destination. Too much fuel, and the rocket becomes too heavy to function efficiently. Somewhere in between is a narrow path where everything barely works. And that path is defined by the equation, and the most unsettling part is how invisible this trap is at first. It hides behind simple intuition, behind the idea that more fuel should always help. But once you see it, once you understand how the ratio controls everything, you realize that rockets are not just machines powered by fuel. They are systems constrained by a mathematical truth. And no matter how powerful the engines become, no matter how advanced the technology gets, that truth does not change. The rocket equation is not something engineers solve. It is something they must live with. Once you understand the equation, the shape of a rocket no longer feels surprising. It starts to feel inevitable. What once looked like an engineering choice now reveals itself as a necessity. A rocket is not mostly fuel by accident. It is mostly fuel because it has no other option. If you look at a rocket from the outside, it appears massive, tall. It's a peep and powerful. But what you cannot see is how little of that structure is actually useful payload. The part that carries satellites, supplies, or humans is often just a tiny fraction of the total mass. The rest, the overwhelming majority, exists for one reason: to solve the problem created by the rocket equation. Most of the rocket is fuel, and even more surprisingly, much of that fuel exists just to push other fuel. At the very beginning of the launch, when the rocket is at its heaviest, the engines are burning fuel at an incredible rate. But a large portion of that energy is not going into accelerating the payload toward space. It is being used to lift the fuel that has not yet been burned. The rocket is spending energy just to carry its own energy source upward. This creates a strange and almost counterintuitive structure. The lower parts of the rocket, the largest tanks, the most powerful engines, are not directly helping the payload reach orbit in the way we might expect. Their primary job is to deal with the massive weight of the fuel above them. They exist to solve the worst part of the problem, the beginning, when everything is heavy and inefficient. As the rocket climbs and burns fuel, it becomes lighter, and the situation improves. Less mass means the same thrust produces more acceleration, and the rocket can finally begin to gain speed more effectively. But by this point, a huge portion of the fuel has already been spent, not on reaching space, but on making it possible to even begin the journey. This is why the payload ends up being such a small percentage of the total mass. It is not because engineers want it that way. It is because the system demands it. Every kilogram of payload requires many more kilograms of fuel just to lift it. And those kilograms of fuel require even more fuel to support them. The chain builds on itself, layer by layer, until the final structure is dominated almost entirely by propellant. And the deeper implication is even more striking. There is no easy way to improve this by small adjustments. You cannot simply make the engines a bit stronger or the materials a bit lighter and suddenly carry much more payload. The underlying relationship does not allow for that kind of simple progress. The gains are slow, and the costs rise quickly. This is why rockets look extreme. They are stretched to their limits, optimized in every detail, not for comfort, not for redundancy, but for survival within the constraints of physics. Every part of the structure is carefully calculated, every kilogram accounted for, because even small changes can ripple through the entire system. It also explains why spaceflight is so expensive. You are not just paying to move a payload into orbit. You are paying to move an enormous amount of fuel whose primary job is to move even more fuel. The actual useful mass is only the tip of the system, sitting on top of a massive chain of energy requirements that grows far beyond intuition. So when you see a rocket standing on the launch pad, what you are really looking at is not just a vehicle, but a compromise, a balance between what is possible and what is required, a structure shaped not by design preferences, but by a fundamental constraint that cannot be ignored. And in that sense, a rocket is not mostly fuel because we have not found a better design yet. It is mostly fuel because, given the rules of physics, this is what the solution looks like. By now, the situation seems almost impossible. The rocket must carry enormous amounts of fuel, but that fuel creates the very problem it is trying to solve. And every attempt to improve the system only makes the burden heavier. If you keep following this logic, it feels like there should be no way out, as if rockets should never be able to reach space at all. And yet they do. So the question becomes, how do we escape a trap that is built into the physics itself? The answer is not to break the equation, because that cannot be done. The answer is to change the situation in a clever way, to avoid carrying unnecessary weight for longer than needed. This is where staging comes in, and it is one of the most important ideas in all of rocketry. Instead of building a single massive rocket that carries everything from start to finish, engineers divide the rocket into multiple sections called stages. Each stage has its own engines and its own fuel, and each one is designed to operate for a specific part of the journey. At first glance, this might seem more complicated, but in reality, it is a direct response to the problem we have been building up to at liftoff. The lowest stage ignites, producing enormous thrust to lift the entire rocket. This stage carries the heaviest load because it must push everything above it, including all the fuel for the later stages. It burns its fuel rapidly, doing the hardest and least efficient part of the work. But then something critical happens. Once its fuel is gone, that entire stage is no longer useful. It has become dead weight. And instead of carrying that empty mass all the way to space, the rocket simply lets it go. The first stage separates and falls away. And suddenly the rocket becomes much lighter. Not slightly lighter, but dramatically lighter. A large portion of its structure is gone in an instant. The remaining stages now have less mass to push, which means the same thrust can produce more acceleration. The system has effectively reset itself. Not completely, but enough to escape the worst part of the weight problem. Then the next stage ignites, continuing the journey. But now, under better conditions, it still carries fuel. It still faces the same equation, but it is no longer burdened by the mass of the stage that has already done its job. When this stage finishes, it too is discarded, and the process repeats. What staging does is break the continuous burden into smaller segments. Instead of carrying all the structure and all the empty tanks from start to finish, the rocket sheds weight along the way. It refuses to carry what it no longer needs. And this makes an enormous difference because it directly improves the mass ratio at each step of the journey. But it is important to understand what staging really is. It is not a way to defeat the rocket equation. It does not remove the fundamental limitation. What it does is work around it, reducing the impact of the worst parts of the problem. It is a strategy, not a solution. Even with staging, the rocket is still mostly fuel. It still requires massive energy. It is still constrained by the same relationship between mass and velocity. But without staging, the situation would be far worse. A single-stage rocket would need an impossible amount of fuel to reach orbit, so much that it would collapse under its own weight before it ever left the ground. Staging is the reason rockets can exist in a practical sense. It allows us to operate within the limits instead of being crushed by them. It turns an impossible problem into a barely possible one, and that is enough. When you watch a rocket launch and see sections falling away, it might look dramatic, even wasteful, but in reality, it is one of the most efficient decisions ever made. Every stage that separates is a piece of the problem being removed. Every drop in mass is a step closer to escaping the trap. So we do not overcome the equation. We do not rewrite the rules of physics. We simply find a way to carry less of the problem with us as we climb. At the end of all this, after the fuel, the weight, the loop, and the equation, a deeper truth begins to emerge, something that goes beyond rockets themselves. What makes spaceflight so difficult is not a lack of technology. It is not a failure of engineering. It is the simple fact that escaping Earth is fundamentally hard. Not just hard in practice, but hard by the very rules of physics. Earth is not just a place we live on. It is a massive object with gravity that reaches far into space. Every kilogram on the surface is held tightly by that gravity. And to leave it behind, you must gain an enormous amount of energy. Not a little more, not slightly more, but enough to completely break free from that pull. And that requirement sets the stage for everything that follows. To reach orbit, a rocket must move sideways around Earth at an incredible speed, fast enough that as it falls, the ground curves away beneath it. This is not about going up, it is about going fast. And reaching that speed demands energy on a scale that is difficult to grasp. It is not something you can achieve with small improvements or clever shortcuts. It is something that must be paid in full. And this is where everything connects. The rocket equation, the weight problem, the endless loop. All of it exists because the energy required is so large. The rocket must carry the fuel to generate that energy. But carrying that fuel makes the task harder, creating the system we have been exploring. The difficulty of escaping Earth is the root cause, and everything else is a consequence. This is why spaceflight feels extreme. The towering rockets, the massive engines, the controlled explosions, all of it is a direct response to a very simple requirement. Reach the necessary speed or fail, there is no partial success. If you fall short, even slightly, you do not reach orbit. You fall back to Earth. The margin is thin, and the cost of missing it is absolute. It also explains why progress in space is slow and expensive. Each improvement requires fighting against a steep wall of physics. You can build better engines, lighter materials, more efficient designs, but the fundamental challenge remains the same. The amount of energy needed does not change, and the relationship between mass and velocity does not become easier. And yet, despite all of this, rockets do succeed. Again and again, they lift off, accelerate, shed their weight, and reach the speeds required to stay in space. This is not because the problem has been solved, but because it has been managed with extraordinary precision. Every launch is a careful balance, a moment where everything works just well enough. In a way, this is what makes rockets so remarkable. They are not powerful because they ignore the laws of physics. They are powerful because they operate right at the edge of those laws. They take a problem that seems overwhelming and push through it, not by removing the constraints, but by navigating them perfectly. So when you look at a rocket, you are not just looking at a machine. You are looking at a solution shaped entirely by reality, a structure that exists because there is no easier way, a design forced into its form by the need to overcome one of the most demanding challenges in nature. Escaping Earth is not just difficult, it is one of the hardest things we ever attempt. And every time a rocket rises from the ground, it is not just climbing into the sky. It is proving that, for a brief moment, we found a way to win against gravity.